So it's a really pleasure to introduce Thomas Alazard from the Ecole Normale Supérieure and CNRS, and he will speak about entropies for free surface flows. So Thomas, please.
Thank you very much for the invitation. It's a great pleasure to talk about for this conference. I'm going to talk about entropies for some free surface flows. And on this picture, you can see two free surface flows, water wave in the far field and some free surface flow in porous media in the near field. And I want to discuss some results about these flows in porous media whose analysis is inspired by the study of water wave. So here I am just zooming in on this part to show you these beautiful patterns. So we are considering a time-dependent domain depending on time t, which is a time t of that form, the set of points x and y in the torus td times r, such that y is strictly smaller than h of tx. Here, d is an arbitrary dimension and h is an unknown function called the free surface parametrization. We denote by sigma of t the boundary, which is the graph of the function h. We also introduce the normal n and Vn, the velocity of the free surface in the normal direction. Vn is given by an explicit computation. This is 1 upon the square root of 1 plus gradient h squared times dth. We also introduce kappa, which is the opposite of the mean curvature. Okay, kappa is the opposite of the mean curvature. Denote by h of h and script h of kappa the harmonic extension of the function h itself and kappa in the domain omega. Okay, I will clarify the notation later. Then we can define three boundary problems. Firstly, the mean curvature equation. This is the equation that stipulates that Vn is equal to minus kappa. The equation Vn is equal to minus dn of script h of kappa, which is the so-called Mullin-Sekerka equation, and the Elliptic equation, which reads Vn is equal to minus dn script h of h. There are three boundary value problems, that is evolution equations that describe the velocity of the free surface in the normal direction in terms of some nonlinear expression depending on the free surface parametrization itself. There are many possible ways to study this equation, and in this talk I'm going to discuss some partial differential equation approach based on exact identities and functional inequalities. I will mostly focus on the Elliptic equation, and I begin by clarifying the derivation of this equation. Consider a free surface flow having velocity v, pressure p, and gravity g equal 1. We normalize the gravity. So think of a free surface flow. Inside, in the bulk of the domain, in the fluid domain, we assume that the fluid is divergent free, divergence of v is equal to 0, and that v is related to the pressure thanks to Darcy equation, namely that v plus the gradient of p plus g plus y is equal to 0. You can compare this with the classical Euler equation. This is a classical Euler equation when the gravity is normalized to g equal 1. And to obtain Darcy equation, you simply replace this convective derivative, dtv plus v dot gradient v, by the velocity v itself. So you, instead of having the incompressible Euler equation, you have the Darcy equation. This is inside the fluid domain. On the boundaries, that is on the free surface, we assume that Vn, the normal component of the velocity of the free surface in the normal direction, coincides with the normal component of the velocity. This is the first equation. And secondly, we assume that the pressure is constant on the free surface. And without loss of generality, we can assume that this constant is 0. Then, by combining these two equations, we obtain directly that the divergence of V is 0, which means that the divergence of the gradient of P plus Y is equal to 0. And of course, this implies that the Laplacian of P plus Y is equal to 0. On the other hand, if you evaluate P plus Y on the free surface, since P is equal to 0 there, you get that P plus Y is equal to H, which means that P plus Y is equal to the harmonic extension of H. Now the equation, the kinetic equation, kinetic boundary condition, Vn is equal to V dot n, implies that using Darcy equation, V index n is equal to minus dn of P plus Y. And since P plus Y is equal to the harmonic extension of H, you get the Elliptic equation, namely the fact that Vn is equal to minus the normal derivative of the harmonic extension of H. It will be convenient to write the previous equation as an evolution equation for the free surface elevation H itself. For that, it's convenient to introduce some notation. Firstly, I recall that given a function f depending on x and y, we denote by f index y equal h the function that evaluates f on y equal h. Also, for the following, I introduce a notation that we will constantly use, the Dirichlet to Neumann operator GH. Namely, given two functions h and psi, which are functions of the variable x only, introduce phi, which is a function of x and y, which is the harmonic extension of psi. By definition, this means that phi is an harmonic function in the domain located under the graph of h, which coincide with psi when you evaluate phi on y equal h. Phi is the harmonic extension of psi. Then, by definition, the Dirichlet to Neumann operator GH is defined as follows. GH of psi is equal to the normal derivative of phi evaluated on the free surface multiplied by this factor, the square root of 1 plus gradient h squared. Now, with this notation, the previous Elliptic equation, Vn equal to minus dn h of h, can be written as follows. In a very compact way, dth plus gh acting on h is equal to 0. You can compare this with the so-called Zakharov-Krekslin formulation to study the water wave equation. The Cauchy problem for the Elliptic equation can be studied by many different techniques, and I am quoting here only a few papers that are devoted to this question. There are papers based on PD method using L2 energy estimate. They are results by Chen, Bill Hu and Lovengrove, Ambrose, Knuffer and Masmoudi, Gunter and Prockert, Chen, Gradero, Bellingham, and Scholar, and many others. You can also study this equation using functional analysis tools and maximal estimates, like in the paper by Escher and Simonet, Proust and Simonet or Mathieu. You can also use tools at the interface of harmonic analysis and partial differential equation. And this is rooted in the work by Cordoba and Gancedo and developed further by Castro Cordoba, Pfefferman Gancedo, Lopez Fernandez, and Gomez Serrano, or Granero Belinchon, Cordoba and Omar Alazard, Gancedo and Lazar. You can also apply maximum principle inequalities, like in the works by Constantine, Cordoba, Gancedo, Rodriguez Piazza, and Strain, Cameron, Cordoba, Lazar recently, and Gancedo and Lazar. Or you can apply comparison principle to study viscosity solution, like in the pioneering work of Kim, and recently by Changlara, Guillen, Schab, or Dong, Gancedo, and Nguyen. Here, I'm just going to explain a quite simple result obtained by several authors recently that states that, firstly, the Elliptic equation always have some smooth solution for subcritical initial data. More precisely, given any dimension D and any index S strictly larger than 1 plus D over 2, for any initial data H0 is in HS, the Sobolev space HS, you can find a time T and a unique solution to the Elliptic equation, which is continuous in time with value in HS, C1 with value in HS minus 1, and L2 in time with value in HS plus 1/2. The last point has to do with parabolic smoothing effect, which implies that for positive time, the solution is smooth, say infinity. In the following, we will say that H is a regular solution, provided that it satisfies this condition for some index S larger than 1 plus D over 2. You can extend this result in many directions, and for example, it was extended by Kangui Nguyen and Patrick Flynn to study the same problem with surface tension, and they derived a uniform time of existence with respect to the surface tension coefficient. I will say a few words about the proof to explain that you can have a very short proof using exact identities. The point is the following. To study the Elliptic equations, the main difficulty is that the Dirichlet-Neumann operator depends in a very nonlinear way on the free surface parametrization. And we would like to quasi-linearize the Elliptic equation to understand the dependence with respect to H. To explain this, let us think by comparison with the Hamilton-Jacobi equation, dtu plus 1/2 of ux squared equal to 0. To study this equation, one approach consists in introducing v, which is the derivative of u with respect to x. Then v solves a Burger's equation, and you can study this equation, a classical solution for this equation using standard tools for linear hyperbolic equation. For the Elliptic equation, you can proceed in a similar way and quasi-linearize this equation as follows. We want to find for the Elliptic equation an analogous result, saying that you can introduce some good derivative that satisfy a quasi-linear equation instead of a fully nonlinear equation. The question is to find possible transformation. This lemma says that there are at least 3 different unknowns that you can introduce, namely, denote by phi the harmonic extension of the function h in the fluid domain. Then introduce 3 functions, a, capital V, and capital Y, which are some derivative of phi evaluated on the free surface. They are derivative with respect to either time, x, or y. Namely, capital Y is equal to dt phi evaluated on the free surface. Capital V is the gradient with respect to x of phi evaluated on the free surface. and A is equal to 1 minus dy phi evaluated on the free surface. Then this lemma asserts that these three unknowns, A, capital V, capital Y, satisfy exactly the same equation. Namely, if you denote any of these three unknowns, U will satisfy this equation. dtu minus V gradient U plus A GHU plus gamma over A U is equal to 0. In this equation, the coefficients are capital V and A, which are defined here, here and here. And gamma is this function defined in terms of H, A, and V. The point is that if GH, if you replace GH by a derivative, then gamma is equal to 0. Of course, GH, the Dirichlet-Neumann operator, is not a derivative, it's a non-local operator, but still you have a kind of cancellation that says that there is a cancellation here that says that this is not like an operator for the one acting on the unknown. It's something more regular, and in particular, it suggests that we can see gamma as a true coefficient. The proof of this lemma is directly inspired by results used to study the water wave equation and can be derived by using Land's shape derivative formula, which was used by David Land to expand computation made by Zakharov and Craig about water waves. It's a way to understand the differential of the Dirichlet-Neumann operator computed with respect to the free surface parametrization. So hence the name, shape derivative formula, which means a derivative when you move the shape. Okay, you compute the derivative with respect to eta. And you have an explicit expression involving the Dirichlet-Neumann operator itself, as well as two quantities, script B and script V, which are given in terms of eta and psi by explicit expression. So once you have a tool to compute the differential of the Dirichlet-Neumann operator, you can compute what is dtgh of h, what is dxgh of h, and hence you can compute the equation satisfied by this and that. The next step of the proof is to understand the nature of this equation, the equations that we obtained for the derivative. The first term is clear. It has to do with the convective derivative. Here we have a coefficient. And so the main question is to understand the contribution of that term. We know from classical result in analysis that GH of H is an operator of order 1, and it is self-adjoint. It behaves like the square root of the Laplacian. So essentially, the nature of this equation will depend on the coefficient A. This lemma says that this equation is parabolic, namely that the coefficient A is positive. The proof goes back to the observation by Sidgwick for the water wave equation that the Taylor coefficient is always positive, and you can prove similarly that A is positive by following the proof by David Land. Namely, the proof is very short. It consists in observing that A is a derivative of the function y minus phi with respect to y, that this function is harmonic, and that it vanishes on the boundary. And then you simply use the Hopf-Zaramba principle that says that the normal derivative of y minus phi on the free surface is positive. Since on the other hand that this function vanishes on the boundary, it's very easy to relate the normal derivative to the vertical derivative, that is the derivative with respect to y, and you get the result. Now we have an equation with a term of order 1, GH. There is another.
Thomas,
yes?
Thomas, just one question, because I think here you have to use some sign condition or something. I forgot, but there is some extra thing that you have to add to deduce that that normal derivative is positive, I guess. No.
For the water wave equation, the proof is more difficult than here. Yeah, it's
no, because here, like, no, because if I follow your proof, I can apply your proof to phi minus y. You need something else in the inside.
Yeah.
You need the sign condition inside.
Yeah, at minus infinity, you have that the derivative of this quantity with respect to y is positive.
Right. Okay. You use the fact that phi decays, and then so there is a sign.
Exactly. You have a sign condition.
Because you see, as your proof goes, I can replace phi minus. I can apply it to phi minus y. So
yeah, you're right. Excuse me for that.
Okay. No problem. So so there's something about the behavior at infinity. Okay. Thank you.
Thank you, Nader. Now we have an evolution equation with two terms of order 1, this one and this one. But for the purpose of proving an energy estimate, this one does not contribute like an operator of order 1. It's rather vague, but it can be clarified by saying that this operator, capital A, which is V dot gradient, is of order 1, but its real part is morally of order 0. More precisely, you can compute that A plus A star acting on some function f is of course equal to minus the divergence of capital V multiplied by f. If V is a Lipschitz function, this is bounded, and hence this is an operator of order 0 on L2, for instance. For us, the situation is slightly more difficult, but because we are not assuming that capital V is Lipschitz. By Sobolev embedding, V will be only an infinity in time with some older modulus of continuity, C0 epsilon for epsilon small enough. But using paradifferential calculus or simply paraproducts, it's easy to justify the fact that A plus A star can be seen as an operator for the 1 minus epsilon. So it's not an operator for the 0, it's only for the 1 minus epsilon, but it's enough because it means strictly smaller than 1, which means that this operator is sub-principal term. And eventually, to study the Cauchy problem for this equation, you need to understand what is GHH, and for that you can use, for instance, paradifferential analysis that we have studied with Guy Métivier and with Nicolas Burke and Claude Zully, that shows that you can replace GHH by modulus of dx, or something more complicated in higher dimension, up to a remainder term of order 1 minus epsilon. And then you conclude the proof by standard energy estimates and interpolation acts. Still about this question about studying the Cauchy problem, I want to mention that the situation is more complicated if you consider the two fluids problem. Okay, up to now we had one fluid and something at rest. If you consider the situation where you have two fluids and an interface separating these two fluids, the situation is more complicated, but there is an essential observation by Cordoba and Gancedo is that you can obtain a beautiful and compact formulation for that problem. Namely, they prove that you can rewrite the problem as follows. dTh is equal to 1 upon pi times dx of the integral of the arctangent of delta alpha h, where delta alpha h is the slope. That is the quotient of h of tx minus h of tx minus alpha divided by alpha. Okay, so this is the slope with respect to the variable x. You compute the arctangent of the slope and you integrate. So it's a very beautiful and compact formulation. And to understand it, of course, we begin by linearizing it. We replace the arctangent by the identity. And now we observe that in this case, dx of the integral over r of delta alpha h can be written by an elementary change of variable as dx of 1 upon pi f of y divided by x minus y dy. Since this is an integral computed in the sense of principal value, the contribution of that term can be neglected. And then you recognize that this is the Hilbert transform of f. So we have dx acting on the Hilbert transform of h, which is modulus of dx of f, where modulus of dx is equal to the square root of minus Laplacian, which is in dimension 1 dx squared. So we can think of the Muscat equation as an equation of that form, dth plus mod dh is equal to some non-linearity. On this formulation, it's easy to verify that it is invariant by the following scaling. The equation is invariant if you replace h by 1 upon lambda h of lambda t, lambda x. For that scaling, the critical space are the space of Lipschitz function, or the space H, the Sobolev space of order 3/2. There are now many proofs that the Cauchy problem is well posed on subcritical spaces. They go back to work by E, Kaflich, Robinson, and Siegel, Ambrose, Cordoba and Gancedo, Cordoba and Gancedo, Cheng, Granigro, Beninchan, and Scholar, and more recently by Konstantin Gancedo, Vitkoy, and Ecole, by Matyok, Dengley, and Lin, myself, and Alazard, or Kangui Nguyen and Benoit Posadet. With Kokung Nguyen from Beijing, we prove that the Cauchy problem is in fact locally well posed in the critical Sobolev space H3R. Not only the subcritical space, but the critical space. So for this equation, we can do better rather compared to the Illustrated equation, in fact. Our proof relies on previous work by Diego Cordoba and Omar Lazar. They obtained a beautiful energy estimate of the following form. d over dt of the h3/2 norm plus the integral of dx x h divided by 1 plus dx h squared is controlled by some quantity depending only on the h3/2 norms times the h2 norm. The inequality is very simple to state, but the proof is very complicated. And in fact, their proof is based on a reformulation in terms of oscillatory integrals and the systematic use of Bezos space techniques. With Kokung Nguyen, our proof is based on a refinement, and we observe a null type property, namely that in every step of the proof, you can replace the H2 norm by this factor, okay, which is smaller because for us, we are not assuming that dx h is controlled in an infinity norm. The main difficulty is precisely the fact that this space is not embedded in the Lipschitz space, so we do not have a control of this term, and in particular, this term does not control this term, so that you cannot close the inequality. But using null type properties all along the proof, in fact, a different proof, you can verify that you can replace this factor by this one. And another argument is that we perform some estimate for a norm depending on the initial data. to define this norm, we
So,
proceed.
Thomas, just one question, if you can just go back. When you say you can replace the H2 norm by that red term, it's modulo other factors, right? I mean, you are saying the null type property. I mean, are you using some sort of null structure, or the fact that the nonlinearity has some special form, or
null type property is just a word to try to explain the method. The method is that every time in the proof we will need to estimate dxxh. Okay. We make appear a factor 1 upon square root of dxh squared. We verify that in the proof every time you have a type of cancellation. Every time you will need to have this factor, it can come with a factor of that form. And it's not something explicit and obvious to see. It's like in null type properties. Sometimes it's more difficult and you have to observe that you have some cancellations.
Okay. But then also you have to pay the H3 half norm, right? Like you are put the power of H3 half is bigger now.
Yes, exactly.
Okay.
Because we have to perform some expansions and.
Okay, thank you.
Thank you. Okay, so we want to estimate for a problem in a critical space, the time of existence does not depend only on the norm, on the critical norm. It depends on the profile of the data. This is well known. And to overcome this difficulty, we estimate the solution for a norm depending on the initial data, which is defined as follows. For any initial data H0, you can find a weight kappa 0 such that this quantity is finite. This is just some very elementary result from Lebesgue integrals. Consider a function h0, which is in the critical space h3 half. By definition of that norm, this means that this quantity is finite. But using some standard exercise in Lebesgue integral theory, you can prove that there exists a function kappa 0 that goes to plus infinity when psi goes to plus infinity, such that this integral is still finite. And the point is that we are estimating this norm for the solution. And we can prove that the Cauchy problem is well posed in this space. Okay, and this gives that the Cauchy problem is well posed in this space. We have later with Omar Lazar and Kokung Nguyen prove that these techniques can be applied to other equations, and we consider the Steiner-Berger equation, this equation here, which is a tricky equation derived by Stefan Steiner-Berger to study the flow of the roots of polynomial under differentiation. And we prove that this equation is well posed in the critical phase, which in this case is H. But in the rest of the talk, I want to discuss some inequalities that have to do with the long time behavior of the solution. I want to apply the previous techniques to study inequalities. I begin by discussing some classical inequalities related to the maximum principle that have been first studied by Kim for the Elliptic equation. It's well known since the work of Kim that there are maximal principles for the function h and for its gradient. With Nicolas Meunier and Didier Smets, we slightly improve this and prove that you have a maximum principle also for the time derivative, for every spatial derivative evaluated separately. And also that we have a kind of maximum principle for the Taylor coefficient A that measure the parabolic effect of the Elliptic equation. Okay? Namely, we have these inequalities. If initially one derivative of h is bounded from above by n, where d is any derivative, then the same remains true for all time. And similarly, if it is bounded from below by minus n, then the same remains true. And more interestingly, this inequality that says that the infimum of A at time t is always bounded from below by the infimum of A at time 0. And the proof is based on the Stumpaka method to prove maximum principles and the identities for the function u that have been stated above. The proof is based on Stumpaka method and some pointwise inequality. More precisely, a variant of a pointwise inequality introduced by John Toland to study Stokes waves, which are fundamental waves in the study of the water wave equation. Toland proves that there is this inequality for the fractional Laplacian. Namely, 2f times the fractional Laplacian acting on f is always bounded from below by the fractional Laplacian of f squared. This inequality was also derived independently by Antonio Córdoba and Diego Córdoba. It can be generalized in many directions, and for instance, there is this lemma obtained by Antonio Córdoba and Martinez, myself and Nicolas Meunier, or Peter Constantin, or variants of this lemma. It states that for any convex function phi, which is C2, let's say, phi prime, the derivative of phi prime of f times gh of f is always bounded from below by gh of phi of f. Okay, so it's a pointwise inequality that generalizes this one for the case of where phi of f is equal to f squared. The proof is very simple. It consists in observing that if you denote by u the harmonic extension of f, by v the harmonic extension of phi of f, and set w to be the difference of these two functions, then of course w is equal to 0 on the free surface, because on the free surface this is equal to phi of f and this is equal to phi of f also. And in addition, you can compute what is minus Laplacian of w. Minus Laplacian of w is equal to Laplacian of phi of u because v is harmonic. And using the chain rule, this is equal to phi prime of u Laplacian of u plus the convex second order derivative of phi of u times the square of the norm of gradient u. This is equal to 0 because u is harmonic, so it remains only that term, which is non-negative because phi is convex, and this term is of course non-negative. So minus Laplacian of w is non-negative. Since minus Laplacian is a non-negative operator, since w is non-negative on the free surface and non-negative in the free domain, you deduce that w is a function which is equal to 0 on the free surface and non-negative inside the domain. In particular, the normal derivative is non-positive, and this means exactly by definition of w that you have this inequality. Okay, this is an important inequality to study the Euler equation, and I will refer to it as the convexity inequality. We are going to use this to study other monotonic quantities. And to clarify the setting, I introduce this definition. Later, given a regular solution H to some evolution equation on a functional I, defined on the space of smooth function with value in R+, we say that I is a Lyapunov functional if it is decaying along the flow. We say that it is an entropy if in addition we have some lower bound for the dissipation rate, which means that we have, okay, it's not only non-positive, we have also an inequality. And I would say that I is a strong Lyapunov functional if it decays like you expect a functional to decay, namely in a convex manner. You expect the functionals to decay in a convex manner, namely the fact that the time derivative is non-positive and the second order derivative is non-negative. Some example to explain this. For example, consider the heat equation. It's elementary to see that the energy is a strong Lyapunov function using the energy estimate and the fact that you can also compute an energy estimate for the homogeneous H1 norm. And by combining this and this, of course, you obtain that this quantity, the square of the L2 norm, is decaying in a convex manner. Something more subtle is the fact that the Boltzmann entropy is a strong Lyapunov function. If you assume that H is positive, so that the Boltzmann entropy is well defined, then you can study the time derivative of this quantity. There is an explicit computation that says that this is equal to minus the so-called Fisher information, which is the integral of gradient H squared divided by H. Furthermore, there are some exact identities that I have found in a paper by Villani that say that dt minus Laplacian of the integrand here is not equal to 0, but this is a quantity with a sign. It's a negative quantity. Okay, there is this beautiful formula. And this tells you that indeed the Boltzmann entropy will decay in a convex manner. It's related to other exact identities which are essential in this field, and I am just giving some name: Li Yao, Aronson, and Benian, that you can find in the book by Vasquez or Vidal. Another example related to the study of free boundary problem that we study with Didier Brecht, namely we consider the so-called Boussinesq equation, dth minus divergence of H gradient H is equal to 0. We prove that for this equation, the square of the L2 norm and the Boltzmann entropy are also strong Lyapunov functional. The proof is based on exact computation as well as a functional inequality, which is valid in any dimension. In any dimension D, you have this inequality with the same constant 9, namely the fact that the integral of gradient theta to the power 4 divided by theta squared is bounded by 9 times the integral of the square of the Laplacian of theta. It's called the Bernoulli type inequality, and they have been studied for this equation and for other equation by Grun, Del Paso, Grun, and Juncker. There are also some other funny Lyapunov functional. For example, for this equation, you can verify that this quantity in dimension 1 is a Lyapunov function. For the Elliptic equation, the main quantity, the main inequality is the energy estimate, of course. It exploits the fact that GH is a non-negative operator. Namely, if you consider the integral of f GH of f, by definition, this is equal to the integral over the free surface of phi dn phi, where phi is the harmonic extension. And since phi is harmonic, you can apply Stoics' divergence theorem to rewrite this as the integral of the square of the gradient of phi. In particular, this is non-negative. Now, if you multiply this equation by h, and you integrate over the torus TD, then you get that the square of the L2 norm is also a Lyapunov functional. It means that the potential energy, this quantity, is a Lyapunov function. This is also, of course, more than that, it's an entropy because we have a lower bound, we can have a lower bound for this thing. And I'm just mentioning a result with Koch and Nguyen. We prove that in any dimension, there exists a constancy so that you have a lower bound for this quantity, even if H is not Lipschitz. It's enough to assume that H has a gradient in BMO. And in this case, you can bound from below this term by the H1 half norm of F. The proof is short, but I'm going to skip it. Other Lyapunov functional are given by the so-called Phi function. Consider a function capital Phi from R to R, which is convex. By definition, the Phi functional is just the integral of phi of H. Then you can verify that the Phi functional is always a Lyapunov function. In addition, if the derivative phi prime is convex, then it's a strong Lyapunov function. Its second order derivative is non-negative. The proof that the Phi functional is the Lyapunov functional is based just on a simple computation. You multiply the Elliptic equation by phi prime of H, and you integrate over the torus TD. You get that the time derivative of phi of H is equal to this, and then you use the convexity inequality proved before to rewrite this in this way, and you further use the fact that the integral of the directed to Neumann operator is always equal to 0. So the fact that it is a Phi functional, it's just a consequence of the convexity inequality. To prove that it's a strong Lyapunov functional requires one more identity, namely the fact that the Elliptic equation can be written in a form of an elliptic equation if you see the problem as in T and X simultaneously. Namely, the Laplacian of H computed with the variable T and X plus some operator BH star acting on the gradient of H squared is equal to 0, where BH star is the adjoint for the L2 scalar product of this operator that associates to psi the vertical derivative of its harmonic extension. The proof of this lemma is based again on Land's shape derivative formula. Then you multiply this equation, not this one, but you multiply this equation by phi prime of H, and you integrate by parts, but not only in space, also in space and time. And you use convexity inequality again to get that the phi functional will decay in a convex manner, provided that phi and its derivative are both convex. The main example of such a function is, of course, the square function. Phi tau is equal to tau squared. In this case, you can in fact compute explicitly what are the first order derivative of the L2 norm. This is, as we have seen, given by this term. And what is the second order derivative in time of the square of the L2 norm? This is the time derivative of this quantity. And using exact identity, again, you can see that it is equal to the integral of A times the gradient of H squared. Now, using the fact that the previous maximum principle for A, we know that A is always bounded by the infimum of A at time 0, which is positive. So we get that the kinetic energy, which is this term, which is equal to the integral of the square of the gradient of phi, the kinetic energy is also an entropy for the Elliptic equation. And if you integrate in time the resulting equation, you get some funny formula that relates a double integral for the initial data, for the initial velocity, to a double integral, but with different variables, t and x, involving h and the function a. Eventually, a nice question might be to try to seek higher order Lyapunov functional controlling derivative of higher orders. And with Didier Brech and Siddhant Agrawal, we obtained some inequalities in that direction. We obtained some pointwise Redic types estimates that are used in many questions in harmonic analysis. So we obtain estimates where the constants only when the dimension is equal to 1 with explicit constant independent free surface parametrization, which is the proof is very simple, but the inequalities might be a little bit surprising. And we also obtain some higher order functionals, namely these two inequalities, which are functional related to the H3 norms. Okay, these are some examples. And another example is an inequality obtained with Didier Brech, and I will finish here. With Didier Brech, we prove that the perimeter is a Lyapunov functional in any dimension. And in addition, there exists some explicit constant depending only on the dimension, so that if initially the slope and GH of H0 acting on H0 are small enough, then we have again a decay in a convex manner with a lower bound for the second order derivative in time of the perimeter. It's related to some computation which are more or less implicit in previous work by Antonsev, Mermanov, and Urinsky. And some different proof applies for the Mullin-Sekerka equation, and then it's related to recent work about the gradient flow structure of that equation by Phi, Almgren, Giacomelli and Otto, and Acerbi, Fusco, Julin, and Morin. For that equation, this gives a proof of the fact that the L2 norm is also Lyapunov functional, which is simple, but apparently it was not new. Okay, but I will finish it. Thank you very much for your attention.
Okay, thank you very much, Thomas. Are there questions? Questions or comment or? So Thomas, yeah, question. Like you showed us those nice picture at the very beginning.
Yes.
Any idea about how we can see this kind of things in this equation?
It's called viscous fingering. And,
yes.
No, I don't understand this.
But you expect that this kind of, I mean, this is like some sort of long time behavior of the equation. So do you expect that the equation has this kind of behavior?
Yes, exactly. But I have absolutely no idea about how to do that and how to understand this beautiful and these beautiful patterns. No.
But are there numerics like so? I mean, this is.
I think I have seen some numerics about that, indeed, some beautiful numerics, but there are some beautiful numerics based on another formulation using holomorphic variables.
Mm-hmm.
Yes, indeed, but I don't remember the name of the author. I'm sorry.
Okay. Okay. Okay, that's good. Are there other questions? No. Okay, thank you all. So we'll question. Is there a question or no? Okay, so we'll meet again at 8 p.m. Abu Dhabi time. See you all.